We're going to go over now and be clear about what from the network flows you really should know, and which parts, the parts I went fast over were parts that I knew I was never going to test you on, right? And I'm going to be clear about that, right? So you can say, yes, I saw it, but you cannot worry about failing the course. All right, now this slide here is a slide, we backed up a bit, is a slide that you should know, all right? The slide is, what does this mean? You should know what the network flow problem is, right? The input is a graph with the node S and T, directed edges with a capacity on each edge, and you need to, you want to push as much flow from S to T such that, what are the constraints? The constraints are that the flow through any edge never exceeds its capacity. So, for example, here we have a capacity of 20, and we have 19 currently going through it. It doesn't exceed the capacity. And two, you look at any node, water's not created or destroyed, right? The sum of what goes in here, 19 plus 2 is 21, equals the flow out, right? Flow in equals flow out. And where that is not true is S. Here where the flow out is 51, and T where the flow in is, actually in this example, flow out is 50, flow in is 50. So the current flow is 50. Right? People get that? And your goal is to find the flow that maximizes the flow into S. So and the algorithm is, a hill climbing, you're given a current flow and you build the augmentation graph. You should figure out how to do this. For here's an example, right? Our current flow is 75. The current flow is 50. You're allowed 75 forward, so that means we can push 75 plus 25 more forward, right? Everybody got that? It's the 75 minus the 50. How much can we push back? Well, we can undo the 50, and then we can do another 10. Right, so the amount we can change in this direction, we're not allowed 60 in this direction because the capacity is 10, right? But we can change the flow in this direction by 60. Everybody kind of get that? So you build, for every edge you build, you do that, and if the edge has capacity 0, then you kind of delete it, and then you look from a path from S to T, and then you look along the path, what's the smallest capacity that you can change? Not the smallest capacity, it's the smallest amount that you can change the flow by along that edge. Right, and here it's 1, and so then what you do is you push the flow through, you add it to where you're going forwards, you subtract it where you're going backwards, and you get a new flow. Alright? So I have never seen a 3101 exam that didn't require you to do that. All right? I'm not saying, maybe because I've never been this clear about it either, right? So maybe I will actually drop it because I know you'll study for it. But that might be cruel and unusual punishment. All right, so now we're given a new flow, right? We're given a new flow, and we do the same game, and we find no path. So now we need to construct a cut. And the cut, and this is a bad example, but the cut, the U side will contain everybody who's reachable from S in your augmentation graph. Everybody who you could change the flow to them. You could push flow along and it would get to them. Right? We're not saying what would have happened to it once it got there, but to there you could get flow. Right? And B are the guys who are not reachable, right? And we know S is here because you can reach S from S, and T is not here because you can't reach S from T, otherwise there'd be a path, right? And then what we're going to prove, no, actually, it's not what we're going to prove. What we proved last class is that when this algorithm stops, if you look at the capacity of this cut. What's the capacity of this cut? You go back to the original graph, right? And you look at the sum of the capacities across, right? Here's a capacity of 31, and this guy has a capacity of 20, right? So the value of this cut is 51. And the key is the capacity of this cut is going to equal our current flow. And why is that? It's because edges going across the cut, forward across the cut, will be at capacity. And any edges coming back across the cut will have zero flow in them.
If that's the case, then how do you have if they're at capacity, then how would you cover more than just S itself?
Right? Suppose it was easy to get through this stuff, right? And it was easy to get through this stuff, right? Then what's our maximum flow going to be? Is this is going to be at capacity, this is going to be at capacity, and this is going to be at capacity, and this will be zero, right? And then when we build our augmentation graph, we won't put any edge here because this is at capacity, right? This will not be an edge. This will not be an edge. This will not be an edge. The reverse ones will be edges because we could undo those, right? And all these guys will be edges because they have huge capacities, right? They're not the problem,
That's the problem.
right? That's the problem. So and then if we say, hey, what's connected to S? It will be this. Right? And these guys are not connected because that's the problem. Does that make sense?
Yep.
That's a good one. We should make a new slide. All right. So what do we go? Our goal here is to prove. Oh, we did all that. That's the proof that we're skipping. All right. So now this is the primal duo idea, which comes up. Sometimes it comes up for min flow max cut. It comes for linear programming in general, and linear programming is something worth knowing. All right, and how does it go? Is I have a primal problem and I have a dual problem, right? And both of these problems have the same input, but they have different solutions, right? And so you think about it, trying to solve the primal problem, in which case I have a solution, some solution to the problem. I have some flow, and one thing we prove is that the value of the primal problem, any solution is always, the primal solution is always less than the dual solution, right? So for any flow, it's always less or equal to the value of the cut, right? You can't have more flow than that can go through a cut. And then we also prove that given a flow, you either get a better flow and a better flow and a better flow and a better flow until you can't get a better flow, at which point you find a reason you can't get a better flow, and the reason is a matching cut, right? And then we stop the algorithm, right? And what do we say? We say, well, I know that the best flow is what I have, right? Why do I know the best flow is what I have? Well, I know I can obtain that flow because I've obtained it, right? And I know I can't do any better because I have a cut which globally proves, no flow can be better. Right? Does that make sense? So those are things you should know about this. All right, now there are some problems to what we talked about. The first problem is, can you get stuck in a local maximum? And in this case, you can't, right? The second problem is, could the running time be exponential? And here's a fine graph, right? Now, what you'd want to do is push flow here and push flow here, and you'd pretty be done, right? But maybe you weren't that smart. Maybe you were dumb. Maybe you push flow there, right? And then you push flow here. And note what you're doing here is you're undoing this flow, right? And then you push flow here and here and here and here. And how many times do you have to repeat this? The flow goes up by 1 each time, so you have to do it a million times, right? And is that a polytime algorithm or an exponential time algorithm? It's exponential. Why?
Because it keeps increasing.
It's exponential in what? The time is exponential in
The size of
the size of the input and the number of bits it takes to write these things down, right? I can put another 0 here, and this input's not that much bigger, but it's going to take you 10 times longer to run it, right? So here's some obvious algorithms. The obvious algorithm is look at all the steps that I could take and take the biggest one, right? This is called steepest ascent. And if you want to know how long it takes to run, then come to the grad class because we cover it next term. But I'll tell you, it's polynomial in the number of nodes in the graph and the number of bits to write down the capacities. All right? Now, before I was born, computer science hadn't really, just before I was born, like as I was being born, right? Computer science hadn't really started yet, and mathematicians and algorithm people weren't happy with this, right? Because they thought of numbers not as something that you wrote down, but they thought of as numbers of one object, right? So they wanted the running time of the algorithm to be polynomial in the number of nodes and edges, and not dependent on the values, right? You could have any values here you wanted. And so one of the problems my father is famous for is proving that if at each time you take, which path you choose shouldn't depend on the values of the capacities, right? Because we don't want it to depend on the capacities. Instead, you take the path with the smallest number of edges in it, then it's polytime in the number of nodes of the graph and the number of edges. All right, so which algorithm in practice would you want to run? Actually, this one's faster, right? Unless your capacities were really, really weird. All right, but still, people were happy with that. All right, so that's just the. All right, so now we're going to talk about linear programming just for 1 minute. All right. Did I say this already to you guys? I had this job, right? It was a job making hot dogs. All right, and so what we had is all these constraints which told you what a hot dog was, right? You could have so much moisture, so much protein in a hot dog, and given today's prices, you wanted to find the cheapest hot dog, right? That meets the constraints. And so what does that look like? Well, our variables were how much pork you put in, how much grain you put in, right? I'm going to put in this many grams of pork, this many grams of grain, and so forth. And we have a cost per gram of pork and of grain and everything. And we have these constraints. So this might say pork has 29 units of water per gram of pork, right? So this will say how much water is being contributed by the pork. And this is how much water is being contributed by the grain. And so, sorry, this was the wrong one. This is how much it costs to make the hot dog, right? Because you're paying 29 cents for the pork, right? So this is how much moisture is. This is how much water there is in pork. This is how much water is in this much grain, and so forth. So this was a joy of PowerPoint. These are less than or equal to's, right? Yeah, you just gotta love PowerPoint sometimes. I don't know why. These slides were great for years, and then about a year ago this happened. All right, so everybody kind of see this? We say you need so much, we have all these linear constraints. So what's key about these constraints is that they're all linear equations, right? You can't have an x squared in here or life gets to be really bad. Everybody with me here? So we get rid of the details, and the problem is we want to minimize this subject to these constraints. And for a long time. All right, so then what's the algorithm for it? It's this primal dual thing, right? That's the best algorithm. And the thing about the best algorithm is that in practice it runs really, really well, right? But given any fixed primal dual algorithm, there is an input in which is going to take exponential time. So that's why people were really upset that it seemed they couldn't prove that this was polytime. But then they came up with the polytime algorithm for it, and actually the polytime algorithm for it's really bad. No one would actually run it. So what people still do is they run this primal dual thing. This was a question on an exam once. It was given an instance for network flows, right? You have a graph and a capacity, right? Write down a linear program which expresses the instance of network flows. How many people do you think got it right?
Zero.
Zero. Zero got it right. All right, so it was not the best question. But it was an easy question. All right? What do we need to say? What are the variables? It's how much flow we had through each edge. Right? That's what we're looking for. What are we trying to maximize? We're trying to maximize the flow into t minus the flow that comes back. Right? Or with respect to s. Right? That's a linear equation. Right? What are our constraints? Our constraints are that for every edge, you don't exceed the capacity of the edge, right? And you have for every node, the flow into the node equals the flow out of the node, right? All linear constraints. Everybody happy with that? So, I thought it was going to be easy, but go figure. I guess it's hard. People have to really understand what network flows are. People really have to understand what a linear program is, and all right, that's the kind of question I'd like to be able to ask. All right, so how does this is a picture which doesn't really do justice to the problem, right? Because here we have two variables, but really we have n variables, so we're talking about a multi-dimensional space, right? And each of the constraints is this plane which says it's linear, so it's a plane, and it says you have to be in there. And our objective function says we want to go in this direction as much as possible, right? So the optimal, you can sort of imagine we're going like this. Our optimal's here. And what is the primal dual algorithm is we start off with some feasible solution, which is a point in here, and it's feasible because it matches all the constraints. And you slide along these edges. You're looking for getting better and better solutions until you get to a solution where you can prove that there's not a better solution because you have a witness in the primal, the dual. The dual sort of sits up there somewhere. It's kind of hard to visualize. In fact, there it is. It is hard to visualize. This stuff. Here's the primal problem. Here's the dual problem. The dual solutions are always better than the primal solution. I made up this picture. It really means nothing.
Are you trying to find the intersection of all the planes then? The point where they all intersect?
No, that would be easy, right? That would be easy because you just use linear algebra to solve them, right? We have far more planes than equations, than variables, right? You have lots of constraints. So they don't all intersect anywhere. In fact, each of these points is where, like if we have n variables, right, then each of these points is the intersection of n different equations, right? And so when you're sitting here, n of the equations are tight, and the rest are slack. They call them slackness conditions. And so as you're moving along here, you're tightening up one constraint and relaxing another constraint, and you slide along an edge. And yeah, as I said, we could take a whole course on this.
You're changing the constraints? Is that what the lines are?
The lines are your linear, these are your linear constraints.
Oh, so how do you make it into the optimal? Like, what are you changing to make it into the optimal?
Let's see, where are our constraints? Right, so we have a lot of these constraints.
So are you changing the numbers, or you can't change the x?
We change the x's.
Oh, okay.
Right, we're looking for values for the x's that satisfy all of these and that maximize these. That maximize this thing. And right, these are all less than or equal to's. Right? So if I told you n of these, if they're n variables, and I told you n of these constraints, and I said they're going to be tight, those are actually equal, then you could solve it and you know what the values of x's were. Right? But then the others have to be slack. But this is far more than we wanted to take in this course. So we're done with this topic. Any questions?
How much sawdust did you try to make hot dogs?
You know, it was all top secret, and I was helping them with the math, but they wouldn't let me see any real equations or any real anything. I saw no real data because it was secret. In fact, I had another job at the same place where if you wanted to copy somebody else's potato chip, right? Somebody put out a potato chip and you thought it was selling well, and then you wanted to make it. How do you do that? You think that would be easy, but there are millions of ingredients that might go into potato chip, and what combination of them gives you this potato chip? And so they would make some recipe and taste it, and they had expert tasters say how close it was. But then if it wasn't close, then you had to try something else. So I had this program where you put in the data of the things that they tried, and then it tried to interpolate and predict what they should try next. All right.
Did it work?
What?
Did it work?
I don't know. I only worked there for a summer. but they were always very happy with what I did for them, even though quite frankly, I didn't work very hard. All right, so greedy algorithms. Any questions about graph algorithms? So, any questions about the test on Monday? Any questions about, this whole course? Anybody panicking about the course? All right, yeah, that's reasonable. So, let me give you another little pep talk. I give too many pep talks around how everybody fails, but the truth is, I've never actually failed that many people. I think every year, maybe one or two, and that was before I started being nasty. So before I started being nasty, as I said, I felt like half the class should fail, and I passed everybody. But now I'm a nasty person, and in the my experiences since then, everybody who sticks it out deserves to pass because I nail it. I try to be really clear what you need to know and what you don't need to know, and people learn it, right? So for example, test 1. The people who didn't do very well are the people who really didn't trust my steps. Right? So, what's the moral here? Is I will fail you if you don't trust my steps. So, trust them. Right? So you will have a test on Monday, and what are you going to say on this test? You're going to say, oh, I have this graph theory problem, and this is the precondition of what I know about the graph, and this is the postcondition of what I want to solve. And I actually don't have to say that because, it's up there in the question. And then I'm going to say, this is my loop invariant, and, chances are I'm going to give you lots of good hints for the loop invariant because I'm nervous about you all failing. And then what are you going to say? You're going to say, precondition and code gives me loop invariant. Then I'm going to say, hey, if the precondition's true, what does that mean? And then what little actions do I do in order to establish the loop invariant? Right? Then you have a new heading, which says loop invariant and code and not exit condition gives me loop invariant. What do? You say I'm at the top of the loop. I know I have these certain values that, variables where I've done in the code so far. I know the loop invariant is true. What does that mean? What does the loop invariant say? All right, then I do these actions. right? I set x equals x plus 1, right? So x double prime equals x prime plus 1. So these are our old values, right? And I know the loop invariant's true for them. These are my new values. I know this relationship, right? So now I have to convince everybody that the loop invariant holds for these, right? And then you have to have a measure of progress, and you have to say, yes, look it, I've made progress when I did this, when I took that step. And then you have to have an exit condition, and you have to make sure that if I make enough progress, then I will exit, right? And then you have to say, if, you have your nice little heading, loop invariant and exit and code gives me the post condition. You write that as a heading. Then you say loop invariant. What do I know because of the loop invariant? Right? Tell me, what do you know because of the loop invariant? Okay, good. Exit condition's true. What do I know because of the exit condition? Right? I do some obvious things to clean up. Right? Now I have to then prove that the post condition's true. Right? What's the post condition? I tell you that. Right? So I'll tell you right now, if you do nothing, maybe no, I shouldn't say this, right? I won't say it. I was going to say, if you can do the steps and say anything at all in there, you'll pass, right? But I don't want, what I often have people do when I say that is they say, oh, I really liked insertion sort, right? So they memorize the proof for insertion sort, word by word, verbatim out of my book. Right? And then I have to say, yeah, they did all the steps. They did all the steps, and they gave me insertion sort. How many marks do I give them for that? Right? I really never know. It's sort of, I'm at loss what to do with a person like that. Right? So I don't want to say that if you just do the steps, you will pass. But you know what I mean. Work with me here. Any other questions? And then recursion is the same sort of thing, you have to know the steps, which are basically trust your friend and don't micromanage them. And now, as far as the algorithms, are, the graphs ones, they aren't really steps because, Andy, I tell you, when I was teaching with him, he would give you guys the hardest graph theory problems. I was like, he would give me his example, we had to have the same test. So he would give it to me, and I would think for 20 minutes about how to solve it, and then think, they will never do that. Never, right? So we would fight about it. And of course I was always right, because everybody got it wrong. All right, but now, so I'm not going to do that, right? The only times I'm going to do that is if it's really a clear, loop invariant kind of thing. The one thing that, if you ever take this class from Andy, what he always did was, if you have a graph, if he gives you a directed graph, that's a DAG. You remember what a DAG is? Directed, no acyclic graph. Do you know what the first thing you should always do with it? What do you do with DAGs? What do we know about DAGs? You can find a linear order. And you can do that in linear time. So every question he ever had was the first thing you do with the DAG is you find a linear order. But that's all right. So what are we doing now? We're now going over to greedy algorithms. Or I closed it. I thought that was never closed. Greedy algorithms. All right. So greedy algorithms is a case where the steps are even more crucial. All right. Why is that? Well, if I tell you a problem and you want to come up with an algorithm for it, the greedy algorithm is the obvious algorithm. All right, so coming up with the algorithm is really pretty easy. You do the obvious things. What is a greedy algorithm? If you see something that you like, you grab it. You think of no consequences for the future. You just go for it. Right? That's the greedy algorithm. Now, does it work? Does it give you the right answer? For most problems, it does not. Right? There's a very small handful of problems in which the obvious greedy algorithm, or maybe a not so obvious greedy algorithm, gives you the right answer. Now, proving that for every input, this greedy algorithm will give you the right answer, what do you think about that? That's the hard part, right? That's hard. And And yeah, I've been doing this for a lot of years, and I have marked a lot of bad proofs. A lot of really, really bad proofs, you know? And so what do I want? I want a good proof, right? That's what I want. I want from each of you a good proof. And how do you do that is, if you look on the steps from the web, what you have is what the proof should look like. And then all you have to do is change things in the appropriate places. Right? And this is another example of don't give me the proof for some greedy algorithm that we do in class, because I want to see that you're making some attempt to change it to the new problem. All right? So this is really what you need. We're going to go through a couple of examples of greedy algorithms and their proofs. And for each one, we're going to follow the same set of steps. And what you have to do is, the details of the particular problem don't matter so much, but you have to understand the steps and kind of why they work. Because, if what you write is almost verbatim from what I say, right? Except you change one word here, literally one word, and I look at that word and I say, that convinces me that they don't understand what's going on, right? They memorized it, but they slipped on this one word, which says to me, no, they don't quite get it. Right? And that's where I'm going to nail you. Right? So you need some understanding. All right. Let's do it. But don't be too afraid. We can do it. Greedy algorithm. Every 2-year-old knows the greedy algorithm is you grab what looks best and you go for it. Right? Remember what an optimization problem is? The input is, you have the set of possible inputs. Each input has an exponential set of solutions. And each solution has an easy-to-compute cost. And given an input, your goal is to find an optimal cost, an optimal solution, right? And some solutions aren't valid, right? So we need an optimal valid solution. Everybody got with this? We did this already, right? And what I try to do is I try to talk fast while I'm not really saying much. And then when we get to the hard stuff, I slow down. So if I don't do that, remind me and I'll slow down. All right, so here's an example. All right, so you go to a game show and there's all these prizes, or maybe it's one of those things, you have a shopping cart and you got to go through the grocery store and fill your shopping cart, right, under some constraints. And your goal is to grab the best things possible, right? So you grab this and you say, man, I've always wanted a lion, right? All right, well, first off, what's a solution? A solution is a subset of these objects. Right? And given a subset of them, you have to make it. In fact, the solution in general is pretty well all the problems we're going to look at. The input is a set of objects, and you need to make a decision about each one. All right? So here the decision is, do I take the crocodile or do I not? Right? So it's a yes/no decision about each one. So that's what a solution is you made a decision about each one. And often it is, I take a subset of them, right? And then, given a solution, right, so some solutions aren't valid, right? Why are some subsets not valid? Well, if you take the lion, you can't take the zebra, right? That's just, there's some constraints, right? So we also specify part of the input is some constraints of what's allowed and not allowed, and then and we have a cost of what a solution is. Often what it is each object will have a cost. The lion will have a value to you, and the zebra will have a value. And the cost of the solution will be the sum of the cost of the objects, right? But we could have a much more complex cost, right? And the goal is to find the best non-conflicting solution. All right, so one option is you try every possible solution, right? You compute its cost. Do we do that? No. Why? Because there are an exponential number of them, right? So the other option is you commit to the object that looks best. Right? So you say, hey, the lion looks good. I'm going to take the lion, right? And you don't worry about the future, right? I mean, you might, if you were really smart, you said, yeah, if I take the lion, then I won't be able to take all the zebras. And if I take the swimming pool, then I won't be able to put in the tennis court, right? All right, so you can, if you were smart, you'd think about long-term consequences. But we're not doing that. We're just we're being a 2-year-old. Right now, the lion looks the best, and we're going to take it, and we're going to commit to it without any thought to the future, right? Right. So the easy part is to locally decide which object looks the best, right? What's hard is to know the global negative consequences of doing that. That's hard. People kind of follow what I'm saying here? All right, so the problem is to choose in best price. We grab the lion. If you take the lion, you can't take the elephant, right? I don't know, do lions actually eat elephants? I don't think they do. That's why I said zebras. But you know, I don't have a zebra in my picture. This is from, anybody recognize this? From Winnie the Pooh. I used to have lots of Winnie the Pooh pictures in the book, and they all came out because of copyright infringements. But I didn't take them out of the slides. All right, that's kind of what I'm saying. You know, you grab things without worrying about the future. And once you grab it, you can't backtrack. All right? So the greedy algorithm, we have two types of greedy algorithms. We have iterative greedy algorithms, and we have adaptive greedy algorithms. All right, so an iterative greedy algorithm is pretty straightforward. You look at each object, you decide how much you think it's worth. You assign a value to it, right? And then you sort the objects according to their value, and you forget the objects, right? Because you're not worrying about the future anyway. And you grab them in order. You grab the first best, the second best, the third best, the fourth best, all right? And as you grab them, you need to make decisions about them. Right? You need to, in this case, you have to decide, do I take it or do I not take it? It could be, do I color it red, blue, or green, right? But you make a decision about it. And the decision, again, is sort of greedy, right? If it's a matter of, if I take the best object, well, sure, I took it because I liked it, so I'm going to keep it, right? You take the lion, right? And then you take the next best with the elephant. Oh, well, do you take the elephant? No, because the lion will eat the elephant, or at least they don't like each other, right? So you go through the objects in the order, and you take them unless you have a good reason not to, unless it sort of conflicts with the decisions you made so far. Everybody understand this algorithm? So as I said, the algorithm's obvious. We could have a recursive form of this, and when we get to recursive backtracking, it really boils down to the same thing, but it's much harder to think about recursively. But the recursive version is you take the lion and then you reduce the instance that you have to the same instance without a lion, right? But you've taken the lion. So, and then you recurse. But let's not worry about that until we get to the next section. All right, so here's a concrete example. For some reason, I'm less anal than I used to be, but I hate change in my pocket, right? And one of the games that I play is to always keep in my pocket the minimum number of coins subject to the fact that I have that much money in my pocket, right? And so that sometimes means when you're buying things, I give them $20 and a nickel and a penny, and she looks at me like, why are you doing this, right? But if she types in, I got $20.06, then the change comes up, and it works out well for me, right? So it's a game, and whatever. All right, so here's the problem, is that you need to make up 92 cents. So when we have our objects, we have an infinite number of quarters, dimes, nickels, pennies out in the world, and we have to choose which ones of these we're going to keep, right? But there are conflicts between them, there are relationships between them, and the relationship is that the sum of what we keep has to add up to 92 cents. Right? Does that make sense? Your goal is to get 92 cents in your pocket. And then what's the cost of a solution? Right? So there's an example of a solution. Right? It happens to add up to 92 cents. Right? Is it optimal? No, definitely not. Right? Some subjects aren't allowed. Which ones? The ones that don't add up to 92 cents. Right? What's the cost of the solution? The cost of the solution would be the number of coins that you take. Right? And sometimes we're trying to maximize, sometimes we're trying to minimize. Here we're trying to minimize the number of coins we take. Everybody good with that? Everybody got what the problem is? Now, you've all lived in this country or in some country for your whole life, right? So surely you've played this game to some extent. You must have some sort of sense on how to solve this problem, right? Anybody want to go how you solve the problem?
You take the quarters,
Take the quarters.
and you add up until you don't go over line.
Right.
And then you take the dimes.
Yeah.
You do the same thing.
Yeah.
And then you do the
Nickels, pennies. Everybody got that? What is that? That is your classic greedy algorithm, right? The greedy algorithm. All right. So the greedy choice, right? Which one looks the best? Well, quarters look the best because they get you to 92 cents as fast as possible, but only give you one cost, right? Your gain per cost is minimized. So it's the greedy choice. So you keep grabbing quarters until they exceed the amount, and then you grab dimes, right? So does this give you the optimal? How many people think it gives you the optimal number of coins? Always. How many thinks it doesn't? How many thinks they have no idea? How many thinks they could never prove it? All right, so it does give you the optimal. Right, here's an example, right? We just kind of go, everybody kind of follow this example, right? We keep grabbing dimes until it exceeds 92 cents, and then we go for nickels, it exceeds, and then we go for pennies, and that's the best solution, right? All right, so that was fun. Everybody liked that. Let's talk about, so we don't get too cocky before we try to prove things. Let's move to a different country. And in this different country, we have a 4-cent coin, a 3-cent coin, and a 2-cent coin, a 1-cent coin, right? 4, 3, 1. And we need to make up 6 cents, right? So what's the obvious algorithm? Is you grab as many 4-cent coins as possible, right? Does this work?
No.
No. Why does it not work?
Because then
Right? Because if you grab the 4-cent coin, you're doomed right from the get-go. Right? That was dumb. Why? Because then you need 3 coins, while 2 coins would have done it.
So now? So now what do you do?
Now what we do. So, here's a completely different problem. The meta problem is I tell you what coins there are, right? And I tell you what you want to make up, and you want to know to minimize, you want to know whether or not the greedy algorithm works, for example, right? That's actually a hard problem. It's quite a hard problem. If I tell you the coinage, and I want to simply know does the greedy algorithm work, you'd think it would be easy, but it's not easy. And in the grad class, people have to give a talk, a 20-minute talk, and one person 1 year gave a talk on that problem, and I was fascinated. It was really quite an interesting problem to know whether the greedy algorithm is going to work or not, but we don't have to worry about that, right? All we're going to do is we're going to observe that here it does not work, and with the quarters and the dimes and the nickels and the pennies it does work. All right, that's as far as we're going.
So why is that? Like, why does it work for one but not the other?
Why? I don't know. I guess why would, if I were going to answer the question, why does it work, then I would, or not work, then I would have to answer, given an arbitrary set of coins, when does it work and when does it not work? And that is a hard talk that we're not going to cover today. So I can't even remember. So no, I can't answer why.
Can you say that the fact that it doesn't work make it to, like, the algorithm that we used for the nickels and the quarters is wrong? Because it doesn't work. It is right for them, for
Right.
that set of coins, but
Right.
it doesn't work for this.
Right, so it's the wrong algorithm in general, and it's the right algorithm if you live in Canada. Right? 5 minutes. All right. Another question?
If we get to send a question during the test, can we solve it?
If I tell you to solve this problem using a greedy algorithm, it will say on the top, greedy algorithm question, and yeah, it will be one that has a greedy algorithm. And that actually might not be true. If I say, solve this with a greedy algorithm, then probably you can. I might give you a problem and say, can you solve this or not? In which case, you'll have to either come up with an easy counterexample like this, or prove that it always works. Right? And you have to figure out which one. But if I do that, it'll probably be reasonably obvious. Like most people, I could hear when I put this up, another number of people sort of immediately kind of saw that. So I'd want one that was easy enough that at least a third of the people immediately would say, yeah, this is pretty obvious.
Wouldn't the like the coins not working in this have something to do with the relationship? Because the 1, 5, 10, and 25, they're all multiples of combinations.
Very good,
But
very good.
it's not. The
So
4
here's-
and 3 don't.
Right, so if each coin was a multiple of the next coin, then it works. It just works.
Times a quarter.
But dimes and quarters,
But 5 to 10. you
yeah,
go
but
5
dimes
to-
and quarters just killed you.
But 5 to 25. 25 is a multiple of 5. So it's
Yeah.
a multiple of some other coin where it's 4.
Yeah, if I have a penny in there, then every coin is a multiple of some coin, right? So,
Your penny.
yeah, so, and here we have a penny, right? So, it's there's some things like that you said, well, if this is true, then it works, right? And, but it's not so clear in general. All right, when does it work? We don't, it's hard to know whether they work. It really is hard to know whether they work. And in general, for most optimization problems, they don't work, but it's a good first place to start. If you're given this new problem, the first thing to do is say, well, what's the obvious greedy algorithm and why doesn't it work? All right, we only have like 4 minutes, so we probably have 3 minutes, so we're not going to get very far. But let's do it. We can go a little bit further in how to prove this. We need a loop invariant. And the loop invariant, what's the algorithm is you're grabbing, in this case, coins, and you're deciding to keep them or not keep them. And, right, so these are our steps, right? The algorithm chooses the best object amongst those not considered so far, and either commits to it or rejects it. And we make progress. Why? Because we consider another object. We're clearly making progress, right? The exit condition is when we've made a decision about every object, right? So a loop invariant is going to make a statement at the top, right, which is always going to be true. Right, and after you commit, let's start with that first quarter, right? What statement do you want to make after you've committed to that first quarter? Anybody can think? I'm trying to make 92 cents. I committed to a quarter. We need a statement.
So, subtract, like loop invariant you're asking?
Yeah.
The quarter is part of the total.
All right, that was pretty good. The quarter, let me reword it slightly. This quarter is a part of the solution, right? So here's one possible loop invariant. The algorithm solution is optimal, right? We've grabbed the first quarter. Is this a good loop invariant?
Yes. Not optimal for the
What is a solution? A solution is something that adds up to 92 cents, right? Do we have a solution?
No.
No, we have a quarter. So we don't have a solution yet. So this is a completely meaningless statement, right? A number of times I've had people write this down as a loop invariant. It's too many to count. Do not give me this as your loop invariant, right? We don't have a solution yet. We have a partial solution. We have a quarter. And so you could say, well, the partial solution is optimal. What's wrong with that? Maybe that's in our next guy here. Algorithm is only committed to one quarter, and this does not. Yeah, that's what's wrong with that one, right? We've only got one quarter. We don't have a solution. All right. All right, here. Well, the sub-solution. What we've done so far is optimal, right? Is that a good loop invariant?
optimal to what?
What does optimal mean? I only have a quarter. What does it mean for a quarter to be optimal? Right? I know what it means for a solution to be optimal. I don't know what it means for a quarter to be optimal. Right? So this is also a bad loop invariant. Right? All right. So more of the input kind of idea says people say, remember more of the input is I've read the first I objects, and if that was the entire input, then I would have an optimal solution. Right? Do you think that works so far? Right? If there was only a lion, what's the optimal solution? You take the lion, right? I mean, that's a no-brainer. That doesn't tell you whether you should take the lion when there are a lot of zebras out there, right? So this is not useful, right? Right? This is the lion example. Taking the lion just does not help us here, right? The intuition, what we want, is that if I take the quarter, I haven't gone wrong, right? Because when I took that 4-cent coin, somehow I knew I went wrong, right? Why did I go wrong when I went to the 4-cent coin? And I don't go wrong when I get the quarter. It's kind of what she was saying, is the optimal solution contains a quarter, right? But it doesn't contain 4 cents. All right. Here's we're saying the optimal solution contains the best object, this quarter. Is that good? All right. Well, here's an example. I got lots of quarters, right? Some solutions contain that quarter over there and don't contain the quarter I just grabbed, right? So there's some sense of, or maybe what happens if there are two optimal solutions, one which contain only zebras and one which contains the line. Is that a problem? Right? The problem with the "the" here, why did I put "the" in quotation marks? It's because there could be more than one of them, right? So this is wrong to say the optimal solution. Do I need to say that all optimal solutions contain the object I've grabbed? No, what do I need? Yeah.
One of the
Yeah. Exactly. There may be more than one of them. They may all contain the chosen option. So this is what we want. At least one optimal solution contains this best object that I've grabbed. And the one way of thinking about it, you know the expression, don't burn bridges behind you? Right? It's okay to burn some of your bridges. Just don't burn them all. Right? And so this, everybody, we're going to stop our class now, but before you go out, read and memorize this. You need to know this. We have not gone wrong so far. Why? Is there's at least one optimal solution consistent with the choices made so far. Right? The algorithm has been grabbing these things and making choices, and there exists at least one optimal solution consistent with those choices. And that's the loop invariant we're going to maintain.
But how do we know that what we're doing is an optimal solution? Like, how do we know the sets of optimal solutions?
Good question. Good question. And that's a very good question, and that's what we're going to have to deal with next time. We're going to have to establish the loop invariant and maintain the loop invariant when we don't know what an optimal solution is.